So how we can explain this root locus nomination in here? Suppose that we have feedback system like RS K divided by S plus S 10. Okay, these are the feedback system. And also you are asked about the find the maximum overshoot. .5% in here. For the solution, we must get that firstly we need to obtain the TS. Okay, this is the GS, right? GS value, and then we can write that the R minus C times G is equals to the what? The C, coming from the what? This feedback system. Okay, and so we can write that the R times G is equals to the C times G, and also we can write that the TS is equals to what? The CS divided by RS for a given reference input to the output, which is can be organized with what? The G1 plus G. Okay, our transfer function is that. And so if we put this transfer function with the what? With the G values in here, and so K divided by S plus 10, and also 1 K divided by S plus 10, and then we will have the K divided by S square 10S plus K. Okay, so these are the closed transfer function. And so if we apply the any RS in here, and then we will get what? The results of the output signal CS, but with based on the what? Based on this closed transfer function. Just remember your midterm or the time response characteristics. If we can use the second order approximation, we can utilize the what? The K S 10S K can be equalized with the what? The omega n square divided by S square 2 zeta omega n S plus omega n square. Okay, so we can assign the what? The K is equals to the omega n square, and also 10 is equals to the what? The 2 zeta times Wn can be inferred that these values. Okay, and so omega n can be selected with the what? The omega n equals to what? The square root of the K, and also 10 divided by 2 times K is equals to the zeta. Okay, so if we have the settable omega n natural frequency and the zeta values, and then we can set this transfer function into the what? Into the maximum overshoot 1.5 overshoot, which is coming from the what? The general solution of the second order system. Just remember that you can use this nomination. And so if we find the zeta values based on what? The K, and so we can have the omega n value in here also. And so if this is the case, and then we can set our parameters based on this information in here, just like this one, guys. So if we choose the proper values of the K, and then we can set the maximum overshoot values of this term in here, just using the different values of the gain in here. This is the proportional control. But how we can design this k value using the root locus. In here, the section 3 is completely related about designing via root locus. Okay, so up to now we can only set the response of the system using the gain adjustment. Okay, gain adjustment. For example, if we have the S-plane in here, just like this one, sigma and JW in here, and so, for example, we have the 2 poles, -2, -1, or 1, 0 value, for example, -5, and so we can write to the what? To our root locus, because at every change these values can be changed in here, just like this one. And so this red line is the proper k value, k proper value for this system, is a settable system. But just remember that if we have the S-plane in here for a given system, and then we can set the system of the percentage overshoot settling time for the for the red lines in here, because at each different k value we can draw these red lines. But these two terms, poles and these zeros, coming from the open loop response, right? Open loop transfer function. But if we apply the k value in the closed loop form, we can draw these lines in here. This is the root locus. Okay, and so we can set any points in here. For example, this one, this one, this one, this one, or this one. But we cannot set this point because our system cannot permit this selection of these roots, right? Because if we want to set our output response based on the gain adjustment, we just use only these red lines in terms of the what? In terms of the k values. And so if you want to select the overshoot, settling time, or the peak time, or the steady state error in here, and so we need to reach all the poles or the values of these terms in here. But if we have only k value in here, we cannot reach every poles in S-plane. And so how can we solve this problem? This problem can be solved with adding compensator to add the pole and zeros to the system, right? Just remember that if we have this nomination, and then we can add the s, or 1 divided by s, in order to in order to change this red line on the root locus. For example, if we have any reference signal in here, just like this one, okay? And so if we have any plants in here, gs, and so cs can be written in here, and so we can add the poles of this system by using the 1 divided by s plus a. And so this a can be chosen as the on this plane, minus a, right? Or we can add another compensator, s plus b. or we can add the b minus p, right? Or we can use the what, the just simple gain in here, k, which is given in the what, in this domain. And so if we are using only k, this red line is same. But if we add the any zeros or the any poles, this root locus is changed or updated based on these informations. But how? How we can choose the proper values of the zeros, b, or the proper values of the a poles in here? Firstly, we must write the some scripts in here before the selection of the compensator design. Okay, week 6, 7 and the root locus. Okay, and clear all and close all, and CLC should be given in here just like this one, and the x1 should be given in here. Firstly, we need to obtain the root locus in here just like this one, week 6, 7, the internal section, m script x. Okay, so firstly we can define the num as the 1, okay, and then is equals to what, the 1, 7, 10 and 0. This represents to the what, the 1 divided by s over 3 plus 7 times s square plus 10 s plus zeros. Okay, so we can create the g as the tf num, and then in here just like this one. Okay, and so if I run this code, we will have the 1 divided by s over 3, 7s square plus 10s. This is the plant equation in here. Okay, and so figure we have the r locus function in the MATLAB in order to what, in order to draw automatically based on the what for a given transfer function in here. Okay, and so we can also give the title in here just like this one, the root locus of gs is directly related to what, the open loop poles, and so k divided by this, the basic representation of this term, s times s plus 2 times s plus 5. If you are multiply these coefficients, and then we will have this characteristic equation in here, s over 3 blah blah blah. Okay, and so we should also give the grid on in here. So if I run this code, and then we will have this kind of graphics in here. So what's the meaning of this? Just remember that we have the 1 values in here, pole minus 2. Okay, and so pole 0 in here. Also we have the 5, right? And so this root locus represents the 3 poles in here, just like this one. See, minus 5, minus 2 and 0. This is based on the this time. So okay, and so we set the k value is equals to the 1 in here because it's the unity k. This root locus change its k values in here just like this one. For example, if I choose these values, and so the system is represented with the what, with the g, the gain is 16, which means that if we are using the k is equals to the 16.6, and so this poles or the system poles is equals to the what, the minus 0 times the minus 0.6 plus 1.50 I, and the damping ratio is represented with the what, with the 0.363, and the overshoot of the system is equals to what, the 20 9, and the frequency or the Wn values is equals to what? The 1.7. See, if we draw the root locus and then we can examine the any points of the k. For example, if the k is equals to the 40, and then the poles must equals to the what? The minus 6.21, which means that this is the desired pole, and the damping is 1. And if the damping is 1, overshoot is 0, and the frequency 6.41. This is the underdamped system response. This is the damped response of your system in here. See that if we use the root locus, and then we can evaluate the whole of the system in terms of the damping ratio, overshoot, or the settling time of your system for a given different the gain ratio, right? And so, what is the meaning of these grids? These grids represents the zeta values of these terms. For example, this is the 0.76, and so I can search this line in here just like this one, and so if I select this one, the damping ratio is the 0.747, right? And so the overshoot is about the 3% in here, right? But if I need to this overshoot value, I must choose the gain is equals to the 6.47 in this case. Bilge, do you understand how can we use the root locus in here? Yes. If we select the k is equals to 6.47, and so our desired pole is equals to the minus 0.82 plus blah blah blah, and damping is equals to these terms, and the overshoot these terms, because if we have this information, and then just see that this k is automatically drawing in the in the root locus. And then if we choose the different k, and so this root locus represents the values of these terms in here, just like this one. Okay, this is the easiest way to set the k value in order to provide the settling time, overshoot, or the peak time, or the another properties coming from the your systems. Okay, and so also we can have the values of these terms in here, just like this one. If we are using the R locus, k values and the poles can be obtainable for the R locus G in here. If I run this code, and then I will have poles and the proper values of the k. For example, the first term is the R locus is given in here, just like this one, R locus k. This is the selection of the k values, and if we are using the minus 5 k value in here, and our pole is the is coming from the zeros. Okay, this just simple. And so if we set the different values of the k in here, and then we can automatically obtain from the poles of this case in here. Okay, so how can we use this information in order to create automatically finding the values of these terms in here? So x2 and the root locus finding closest zeta values. Just remember that we need to 1.5 overshoot in here. Firstly, numerator is the 1.5 in here, and denominator can be assigned with the what, the 1, 11, 10 and 0. This is the example transfer function in here, okay? And G, T, F, num, and then should be given in here, okay? And so if I run this code, we have, for example, s plus 1.5 divided by s square, s over 3 plus 11 s over 2 plus 10 s transfer function in here. But if we adjust this transfer function in the closed loop functions, and so we must multiply with the k. But which k? Which is coming from the root locus. And so percentage overshoot can be defined with what? The 1.5 100, right? This is the our desired overshoot, okay? So how can we calculate the zeta values based on this information? SQRT, right? SQRT log PO over 2, right? These are the solution of the zeta. It's coming from the time response characteristics of these terms, right? And also we can give the pi over 2 plus log PO over 3, 2, okay? This is coming from the what? This is coming from the time response of the second order system approximations, okay? And so if I run this code, and then in order to create the 1.5% overshoot, maximum overshoot, we should select the zeta as equals to the what? The 0.8007, okay? These are the case. And so how can we do that? The k and the poles can be given with what the r locus values of the g in here, just like this one. And so if I run this code, and then we will have the k values and the poles values in here, just like this one. Just remember that these are the poles for a different k values, just like it's given in this one, okay? So how can we analyze this value? Figure our locus G, and the title of the what? The root of locus, root locus with zeta line. And hold on. And sgrid is another function for the what? The zeta, these values, okay? This is the natural frequency, but we must pass the empty values in here, okay? And so if I run this code, the sgrid zeta is the desired zeta, right? And so just see that bilge, we have this line in here, and also we have the pole location just like this one, this red line, green line, blue line, and another line, okay? So how can we determine the true values of the k in here? For example, if I choose the r selection in here, firstly this line is intersect with this line, and so if I push the left click in here, just see that if we are using the gain is equals to what? The 39.5, and so the overshoot is coming from the what? The 1.5 with the damping ratio of the what? The 0.801. See? So if we want to build the overshoot, maximum overshoot at the 1.5, we must choose the gain as equals to what? The 39.5. Do you understand, Bilge? We can use that. This is root locus. Okay, but this is not the one case because we have the another intersections in here. See, Bilge? We have the intersection of these poles, just like this one. If we are using the another pole or gain as equals to 12.9, and so we have also 1.5, but with a different natural frequency. Or we can use the another pole in here, 7.25, with the damping ratio of the 0.8 and overshoot 1.5, but with the different frequencies. What is the difference? Yes, always you must choose to what the overshoot 1.5 we have choose the gain of these terms. For example, if I choose the 7 or 12 or the 39, and so always our system generates the maximum overshoot at a rate of the 1.5. But what is the difference? These three K values. Just see that the frequency or the natural frequency are different, which means that if I choose the gain 7, and so we may have the different setting time. If I choose the 13 in here, and so we have the different setting time. Or if I choose the what? 39, we have different setting time. But if I choose the K value at this 0.8 line, always our system generates to the what? To 1.5 overshoot value in the closed loop response. Okay? Do you understand that, Bilya? We can use this three gain value in these conditions. Okay, and so how can we automatically find these values? And now we should program it. 3, and in the second order approach, we must approach to automatically find K for the what? The 1.5 overshoot. Firstly, we must define the, for example, the numerator is equals to what? This the different system 1, and the denominator is equals to what? The 1, 10, and 0. Okay, and G is equals to what? TF num then. Okay, and so these are the system, and also we can copy of the whole of these things in here, just like this one. It's the same. Okay, and then the zeta is also calculated in here, and after that we need to obtain the whole the K values and the poles, related poles, the R locus G value. Okay, and so we can figure the R locus G and ascrete zeta and the natural frequency in here, just like this one. Okay, and so if I run this code, and then we will have what? Our response in here, just like this one, 39, and also 39, right? These are the what? The response. But if we have the whole K values and its pole values, and then how we can obtain the R closest zeta value in automatically. In order to do that, so we need to initialize the R variable in here, just like this one. Firstly, closest zeta value is assigned with the infinity values in here, and so we must use the selected K value as 0, and we must also select it omega n value as equals 0. We need to search the whole parameter within the what? The K and the poles in automatically. Okay, and so for K is equals to the 1 0.001 increment in here up to what? The 50 values. Okay, we need to search the whole the K values based on the what the closest response of this system. Okay, and so in order to obtain the closed loop response, we can use this nomination. CLTF is our variable in here. If we are using the feedback function in here, K times G, this is the open loop response. But if we are feeding the unity step response in here, just like this one, we can create the closed loop response to our system. And so this is the plant with the gain. And so we must unity feedback in here, just like this one. And so CLTF represents the what the closed loop response of the our system. Okay, and so how can we obtain the relation or the zeta and the Wn values of these coefficients? Wn and zeta I and the infinite parameters in here, just like this one. We can use the damp function in here, CLTF. Okay, and so if we build these values, and so we can use the damp function in order to what the omega n and zeta I values in here, just like this one. And after that, if we have the omega and zeta values for the closed loop transfer function, we need to create the mean, diff, and idx values for the what the mean function of the absolute values of the what the zeta I minus zeta. Because this is the desired zeta, this is the closed loop transfer function zeta, and so if I search the whole values of the absolute in this domain, and so we can find the minimum values, which means that this creates the what the minimum difference, and the in this of the r what the response in here. Okay, just simple. And so if the mean difference is smaller than closest zeta, and then closest zeta must be assigned with what the mean diff, right? And selected k must be assigned with the k, because at each k we have different responses, and the selected omega n must be assigned with what the omega n idx, right? So this is our response of these systems. And so we can search it at every time. And after that, if we find these values, this can be written like the automatically selected gain k is equals to the what is equals to these terms. Num to str, numeric to str values, selected k, right? And also we can find to what the natural frequency Wn, right? And so the selected Wn, and also we should give the what the rot sec. Okay, so if I run this code, we search the whole area of the R algorithm in here, and so we can search the what the proper k values in here, just like this one. It took minutes to search the every k values, because we test the every k value in the closed loop transfer function in order to what, in order to find out the proper zeta values. Our desired zeta is the 0.8, and we can search the whole data to find out the what the k values. Just see that the proper values of the k is equals to what the 38.989, and the omega n value 6.24, right? And so also you can check the what the root locus in here, just like this one. You can select it, but in this case we can use the r locus output parameter to what to find out your response automatically. Okay, and so how can we prove that? See that CLTF can be utilized with what with the feedback, but with some difference in here. The selected k times g must be given to the parameters in here. Okay, at this case we can search it, and so figure we must apply the step response CLTF in here, just like this one. And so the title can be assigned with the what? The step response, but K is equals to the what? K is equals to the num to str and selected K, right? And so we must use the what? The grid on in here, okay? And so also we can write the settling time as equals to the 4 divided by zeta times selected omega n, and the peak time can also be given in here, just like this one. The pi selected omega n, right, times sqrt 1 minus zeta over 2. Okay? Can write it. And so, if I run this code, and then the R algorithm find the closest zeta value for a given the condition of the what? The 1.5 overshoot. And then this selected K value is feeding to the system with the feedback mechanism. And then we will examine the R results based on these informations. Okay? Just see that. It takes time, guys. Okay. So, this is the R root locus in here. And so, this is the step response of the R system. Just see that. If I choose the what? The peak response in here. And so, if I choose the what? The what? The overshoot 1.5. See? The R selected K represents the what? The 1.5. And we can set these values based on the what? The R locus or the root locus techniques in here. And also we can get the settling time in here just like this one, 0.6, and the peak time is the what? 0.83. And so if we look at this one, the settling time is equal to what? The 0.8, and the peak time is the 0.83, right? 83, and this is the 0.603. Okay? So any question, we can set it based on this information, but for example, if I choose the what? The 20 in here, just like this one. And so if I rerun this code, and then the our response is changed for a given K value, and see that automatically I can find it in here, just like this one. And so, see that this K is equals to what? The 50. It's maybe our system does not reach the overshoot 4.33, because in the root locus, see that in the root locus, our system cannot generate the what? The K values with the what? With the 50. See? 58.5 in here. But if I choose the what? The proper values of the overshoot 5%, 52 must be searched in here. And so if I change the code of this one, 52, 55, and so if I rerun this code, and so we can get the exact values of the overshoot in here. Okay? Just like this one. Peak response 56. I'm sorry. This must be equal to what? 5, because we don't have the 20% desired overshoot on the root locus. Our system cannot design to what? To create this one. See that? The proper values 52, right? The peak response is equalized to what? The 5% in here. Okay? Okay. So any question? Bilge? Okay. So in this domain, we have the closed-loop transfer function, CLTF, as equals to the what? This one. This is the second order. And so, you just remember that. In the second order system, we can approach the second order approximation with the what? With the omega n square divided by s square plus 2 zeta omega n s plus omega n square. And so, which means that we can set the exact settling time, exact peak time, exact steady state error. But what if we have the third order system? For example, x4, okay. If I change the null values in here, just like this one, 1, 1.5, 1, 11, 10, and 0. This is the third order case in here, 1.5. Okay, and so the rest of them is the same with the previous one. Okay, 1, 2, 50 values, and so we must choose the what? The zeta or the desired overshoot as equals to what? The 1.5. Okay, and so this is the third order system, just like this one, s plus 1.5, s over 3 plus 11 plus 10s. Okay, and so if I run this code, just remember that this is the second order system, but this is the third order system. We cannot match the exact representation of the second order approach in this case. But our algorithm is run in here. Okay. See, this is the what? This is the third order response of the R system. But we have the K is 39.56, and so we can search the peak time in here just like this one. The overshoot values of the what? The 9.51. What is the difference between these values in here? Just like this one. We set the 1.5, but we get 9.51 because we cannot easily set the what? The third order system with the second order approximation in here. Just remember that if we can add the pole and the zeros of the R system, we can get the fastest response in the R transient response. In this case, if we have the third order approach in here, and then we may not have the proper solution for these overshoot values. For example, we don't have the what? The proper values in here, just like this one. But just see that for this system, we have this transfer function in here, just like this one. And so we can say that these values in here, the overshoot 1.5 for this transfer function. But just remember that this overshoot 1.5 is given for the what? For the second order system approximations in here. Okay? And so just look at to the what the R looks again in here. (39.5), and so these are the roots, and then this CLT feedback system can be changed 39.5. okay, and so if we rerun this code, and then we will have the what the characteristics of the what the peak response in here, but the overshoot 9.5. What's the difference between this system with the previous one, Bilge? Why we don't have the exact representation of these overshoot values in here? Why? Just answer me. Yes, definitely. You are true. If we are using the higher order system representation, we cannot set the proper values of the closed-up transfer function in here. Okay? So, for example, if I choose the what? The 38 values in here, for example, see that the peak response 9.25 or 30. See, in the closed-up transfer functions we have, for example, the peak response is equals to 7.81, right? And so if we have this information in here just like this one, and so we should say that if we have this nomination with the third order approach, and then maybe we should set the what the transfer function with these nominations in here just like this one. In the 20 we have the 6.37, okay, or just draw this one in here, okay, and also check the other poles in here. Just see that 13, just see that 7, right? And so maybe this K gain, due to the third order approach, this K gain must be equals to 13 or 7 in here. Just write in here 13, and so the characteristics is equals to 5% in here. Still we could not achieve this parameter, or 7 peak response. See that this is the best way to what to overshoot in here. So we must understand that if we have the higher than the second order system, you must assign your system with the what, with some additional parameters based on this information, if you are only using the proportional gain. Did you understand what I'm saying, Bilge? Because it's important. If you have the more than second order system, we can use still the second order approach, but we cannot match easily these two response in the closed loop one. Okay? Okay. And so let's take a break, and at the 2:05 p.m. we will start the new lesson.